As we look at section 2.2, we need to look at some rules. This whole section is going to be on what are some just standard rules for taking derivatives. If we have to go through the limit process every time we take a derivative, then that's going to get very tedious. And when we get to a problem that is more complicated, where we're using derivatives to do lots and lots of different things, we don't want to have to spend a whole lot of time just getting the derivative when the emphasis is on what are we going to do with that. So when we begin, let's look at what happens if we have a function that's a constant. For example, 7. If we want to take the derivative of that, think about that y equals 7 is a horizontal line. So if we were to try to get the slope of a horizontal line, regardless of where we are located, the slope is always 0. If we pick a point here, the slope is 0. If we pick a point here, the slope is 0. Here, the slope is 0. So when we take the derivative of not just 7, but any constant, the derivative of any constant is 0. I think this book uses c for a constant instead of k, but either way, the derivative of a constant is 0. All right, what if we have x to a power, like x squared, x cubed, x to the 4th? Well, if we want to take the derivative of these, it turns out that instead of having to go through that long definition, that the derivative of this comes from bringing the exponent out front and then reducing the exponent by 1. So if it's x cubed, we bring the 3 out front, x to the 1 less power, 2. The derivative of x to the 4th, we bring the 4 down, x to the 1 less power, 3. Even if we had just y equals x to the first power, if we think about our power rule, when we take the derivative, we're going to bring the exponent down front. We're going to subtract 1 from that exponent. Well, 1 less than 1 is 0. Anything to the 0 power is 1. So we would get 1 for that. So the power rule, what we call the power rule, it's just this. X to a power, and it's specifically our variable, not more than x, not 3x, 4x, 5x, but exactly x raised to a power. You bring the power down front, we keep our base, and we take away 1 from the exponent. So that'll give us the derivative when we have a power. Now, as we go farther and farther and farther, then we're going to get into, well, what happens if we have variables multiplied together or variables divided, things like that. But for right now, we're going to be pretty limited. So we have the derivative of a constant by itself, the derivative of our variable to a power. In general, if we know the derivative of some function, if we were to multiply that function by a constant, as long as we know the derivative of the base function, then we just take the derivative of the function part and keep our constant out front. We'll look at some examples of this later, and we're not going to go through a proof on this, but just if we know how to take the derivative of the variable part, we take the derivative of it, and we leave our coefficient in the front. The other rule that we're going to look at for this section is, well, what if we have things added or subtracted? Well, if I have pieces that are either added together or subtracted, and I know how to take the derivative of each piece of those, then I take the derivative of the first term, I take the derivative of the second one. If they're added, I add them, and if they're subtracted, I subtract them. So that's going to allow us, once we get more and more rules for taking derivatives, as our functions get more and more complicated, if we know how to take derivatives of individual pieces, then we can develop functions that are even more complicated, but we can still get the derivatives of them. So we're still limited to an extent on what we can do, and there are lots of functions that we deal with that we haven't run across yet. So let's look at some examples of what we can do, and then maybe look at some of the limitations of the rules we have so far. So if we look back at our rules, there was no rule that involved a square root or a cube root. We only have the derivative of a constant, the derivative of x to a power. If we have something that we know how to take the derivative of it that has a coefficient, we leave that coefficient alone. And if we have things added together. But in general, we just have the derivative of a constant and the derivative of x to a power. Didn't say anything about any square roots. Well, we can rewrite this function. If we have a radical, we can rewrite it with a rational exponent. Remember, our denominator tells us the root we're taking. The numerator tells us the power. So if x is to the first power, we put a 1 on top. So even though this exponent is not an integer, our power rule still works. To take the derivative of this, we bring the exponent out front, and then we take away 1 from that exponent. So exponent out front, subtract 1 from the exponent. Well, if we're taking away 1, that's 3/3. So 1 minus 3 is -2. So this would be x to the -2/3. That's okay like that. Often we like to get rid of the negative exponent, so we can move the x to the bottom and make it to the +2/3. And since our original problem was in radical form, let's put this in radical form. So 3 is not part of the base. Only x is part of the base. So we're going to take the cube root of x, and then that's to the second power. X squared, cube root of that. So that's what we would get when we apply our power rule. The rest of this is just simply algebra. All right, what about this one? We don't have a rule yet for dividing. So how are we going to handle that? Well, let's start out by rewriting this. Let's pull the 7 out front, and let's move the x to the 4th up top and call that x to the -4. So these two things are equivalent. We could move the x to the 4th up top, x to the -4, and then we could pull 1/7 out as our coefficient. So our rule says that if we want to take the derivative of that, if we can take the derivative of part of that, and then we have a coefficient, we leave the coefficient alone, and then we take the derivative of the function part. So this is the power rule. Bring the exponent down front, x to the 1 less power. So take away 1 from the exponent. So exponent goes down, subtract 1 from the exponent. So this would give us a -4 on top, a 7 on bottom, and that's x to the -4 minus 1 is -5. Let's get rid of that negative exponent, so let's move that back to the denominator, and that'll be x to the 5th on bottom. So that'll be taking the derivative there. So while we don't currently have a rule that deals with dividing, if we can rewrite it in a form of something that we know how to take the derivative of, in this case, x to a power, and then if we have a constant, we leave the constant out front, take the derivative of x to the power, that is something that we have a rule for. Where we get in trouble is trying to do things that we do not have a rule for. For example, if we took this same function and we said, well, I'm just going to take the derivative by leaving it where it is, and I'm going to take the derivative of x to the 4th on bottom, that would give us 1 over 28 x to the 3rd. That doesn't work. Notice that's not the same thing. So don't just think, well, if I have something on bottom or wherever it is, I can take the derivative. It has to be able to be expressed as our variable to a power times the constant out front, and that's not in the denominator. All right, what about this one? They say find the slope at this point of that function. So how do we get the slope? We need to know the derivative. Well, how do we get the derivative? Well, we do not have a rule for having more than just x to the second power. If that is x to the second power, we have a rule for that. But we don't have a rule right now for more than just x to a power. So how are we going to handle that? Well, we can do some algebra to rewrite this. If we FOIL that out, 7x plus 2 times 7x plus 2, we would get the first term squared. So 7x squared, 7 times 7, x times x. We would get their product twice. So 7 times 2, that's 14x twice would be 28x. And then the second one squared. So this is the same function. We haven't taken the derivative yet. We have just rewritten our function into something that now we can take the derivative of. We said if we have different terms, we take the derivative of each piece separately. Let's use some of our notation. So if I want to take the derivative of that with respect to x, x is our variable. So when we take the derivative of y, we call that dy over dx. That's just another way of saying y prime. On the right side, we're going to take the derivative of each term. So the derivative of 49x squared plus the derivative of 28x plus the derivative of 4. Now, every term that has a coefficient, we can pull that coefficient out front, and then we can take the derivative of the function part, or the variable part. So I'm going to call this instead of y over dx, I'm just going to go back to calling it y prime. 49 out front. When we take the derivative of x squared, bring the 2 down, x to the 2 minus 1 power. When we take the derivative of x, I'll show that again, but remember we did that earlier. Bring the 1 down, x to the 1 less power, and then the derivative of any constant by itself is 0. So let's see what that gives us. 49 times 2 is 98, x to the first. 28 times 1 is 28. 1 minus 1 is 0, so this is x to the 0, which is just 1. So 28 times 1 is 28 plus 0. So this is our derivative. Now remember what we were asked for. We were asked for the slope at the point 0, 4. So if we want to know the slope at 0, 4, we simply take our derivative and we substitute a 0 in for x. 98 times 0 is 0. So we get a slope of 28. When x is 0, we get a slope of 28. So multiple terms, break them apart, take the derivative of each piece. If we have a coefficient, bring it out front, take the derivative of the x to the power. Coefficient out front, derivative of x to the power. Now in the future, when we do the derivative of x to the first, we're just going to know that derivative is 1. So we're not going to actually go through writing the whole power rule for that one. We're just going to say that's 1. All right, here's another one. If we try to take the derivative here, again, we did not have a rule for taking the derivative if we have a quotient. So we need to rewrite this in a way that doesn't have a quotient. So since we're dividing by a monomial, we can take each piece and divide it by the denominator. So our function can be rewritten as x minus 1, and let's call that last term 8x to the negative 2. 8x to the negative 2 because we have to get that out of the denominator in order to differentiate it. So now if we want to take the derivative, we take the derivative of each term. The derivative of x minus the derivative of 1 plus, we can pull the 8 out front, and take the derivative of x to the negative 2. So we said that the derivative of x by itself is 1, the derivative of a constant by itself is 0, and for this last term, bring the negative 2 down, x to the 1 less power. So we're going to get that our derivative is 1. 8 times negative 2 is negative 16. Minus 2 minus 1 is negative 3. Remember, order of operation, we would have to multiply this before we subtract 1. So we're not going to do 1 minus 16. Now we can do 16 over x to the third. We could write it this way. Or if we got a common denominator, we could turn that into x cubed over x cubed. So x cubed on bottom, x cubed minus 16 on top. So it would be okay to leave it as 1 minus 16 x to the negative 3, or move that exponent down. But that last way would be a good way to write that. All right, the last question I'm going to work through in this video is finding out where our tangent line to this graph is 0. I said 0, where it's horizontal. Where is the tangent line to this graph horizontal? And the reason I said 0 is because what do we know about horizontal lines? That's where the slope is 0. So we need to find out on our function, if we look at all of the points on it, when will we get a tangent line that has a slope of 0? So what do we know about tangent lines? Or how do we find the slope of a tangent line? We need to derivative. So for the first term, we bring the 2 down, x to the 1 less power. The derivative of a constant is 0, so our derivative is 2x. So for any number, for any x, we could plug that in and find out what our slope is. But we want to find out when is our slope 0. So set 2x equal to 0. If we divide both sides by 2, we would get that that's true when x is 0. If we think about that, our function looks like this. That's a parabola that's shifted up. And if we look at the vertex is where we have a horizontal tangent line on a parabola. Where is that? That point that occurs when x is 0. Now, if they want to know the y-coordinate of that, we would have to substitute that back in to the original function, and we get that the y value is 4. So when x is 0, we have a slope of 0, and the corresponding y is 4.